All right. Hello, everyone. Welcome to week 4 and our final week of our Artificial Intelligence for Medical Student workshop. So this week, we'll talk about more of the advanced and state-of-the-art techniques, namely neural networks and convolutional neural networks. Of course, at any point, feel free to ask questions in the chat. I'll try to monitor the chat as best as I can, or just speak up and ask any questions you want. So now, waiting for the slide to advance. Okay, so today we're going to talk about neural networks, which is the big buzzword when people say artificial intelligence, specifically also convolutional neural networks, but we're also going to talk about when they're appropriate and not, because as much of it as it is a buzzword, I've only used neural networks for half of my research projects, right? So there are strengths and limitations to them. And then we'll give some examples of the literature and then our programming example. So the analogy motivation for neural network is like a neuron in your nervous system. There's a cell body, there's an axon where the action potential propagates and it reaches some axon terminals to activate other neurons. So researchers look at this and they think, hey, what if we make a mathematical model based on this? In that we have some sort of input data that goes into a neuron or a kernel or a mathematical function. All these are used interchangeably. I'll call it a kernel because that's what's most commonly called in math. So what if we have a lot of input data going to a kernel and this kernel does some math on it? Let's say if the input is above 0.5, then the output is 1, for instance. And then the output would feed into a lot of other neurons. So then they're thinking, okay, now we can somehow use the input data, manipulate it in some way so we can have some meaningful output, right? So what this looks like in practice is something like this. For instance, we have input data. Let's say if you have hypertension or not, and if you have diabetes or not. And then you have what's called hidden layers. These are kernels where the input is fed forward to. For instance, this neuron is fed to all 3 layers. This neuron is fed through all 3 of these kernels. And then within this, some mathematical operation happens, right? You don't have to worry about what operation happens. The AI researchers will decide what the best mathematical function to insert to these intermediate kernels are. And then there's some output. And then that output is aggregated to make a prediction. For instance, if this is predicting the presence of coronary artery disease, right? So it's a bit complex, but what I want everyone to appreciate is that because of this complexity, you can model some things that are highly complex in terms of interdependencies between the variables. So because these intermediate layers are affected by each of the input layers, and each of the input layers are weighed by a certain amount. Now, how does this optimize and able to complete complex tasks like self-driving cars? Well, these weights in between are constantly adjusted. So remember in our paradigm in machine learning, we pass some training data through, and then we look at what the model predicts, and then we compare with the actual ground truth. So when the model sees that it made an error, let's say it made a wrong prediction, it'll go back and it'll update these weights in a direction which this error will decrease by using some clever vector calculus. So that's in a nutshell how a neural network works. It's quite complex, and you don't have to worry about the math. Only know that it's very good at detecting complex interdependencies between input data. So this in practice is what a potential neural network could look like for, let's say, predicting coronary artery disease from your input data. Let's say all your input data, let's say this is BMI, this is your presence of hypertension, this is hyperlipidemia, and all these input variables are then fed forward to these intermediate hidden layers. These hidden layers perform some sort of calculation on them. And how it calculates is constantly adjusted automatically. So we don't have to manually specify the weight of each of these branches. The neural network algorithm will do it by itself. And then in the end, you get some output. Let's say this one node is coronary artery disease, and this other node is non-coronary artery disease. So if this one node is 1, this bottom node is 0, that means the network's predicting based off all these input features that the patient has coronary artery disease. So that is, in practice, what a neural network looks like. So what's important isn't so much the intermediate math, it's knowing when it's useful. And we'll see an example of that later. It's good at sensing really complex variable relationships. It's good for variables that are complex to even look at by the human eyes, like medical imaging. Quantifying ultrasound texture is the radiologists are good at just salting that, but humans aren't very good at consistently quantifying texture. Let's say abnormal texture. What does that mean? Like, does that mean inhomogeneous? Does that mean skewness? We're not good at that. But the downside, the big downside is that a neural network is not very intuitive. So for instance, all these intermediate layers, let's say you take hypertension, and then the result is that, well, if hypertension is above 0.5 and hyperlipidemia is below 0.4 and the product is below this, and then their derivative is above this, then it's likely to be coronary artery disease. See, that combination of math is not intuitive. So this contributes to what a lot of people call the black box effect in artificial intelligence, which a lot of clinicians don't really like because it seems to fragment the engineering and the medicine. So now next, what you hear a lot in the news are convolutional neural networks. So this is a huge buzzword. You'll hear this all the time. You'll see this in papers all the time. What's important to know, it's even an even more complex scaling up of neural networks. So in this neural network, each one of these kernels is one math equation. Let's say it multiplies the input by 5. In a convolutional neural network, your input is usually a matrix. So let's say an image. An image is a matrix of numbers. And then each kernel is another matrix, which you multiply the input matrix with. So instead of one value, if your image is 500 pixels by 500 pixels, then you have 25,000 values. So you can see how it scales up to be more complex. But the idea is that these kernels will perform a mathematical computation on a segment of that image and then produce something meaningful. For instance, one kernel might extract the top left corner of the image. And maybe the top left corner of an image is really, really important. So this is an example of what a convolutional neural network could look like in practice. Pretend we're trying to predict if the picture is a cat or a dog. So our input is some image, right? Let's say in this case, the image of dog, where our first layer will detect the pixel intensity values, right? They're just, let's say it's just a matrix of 1 in somewhere, which will detect the intensity of that segment. Well, the second layer might detect edges. It might be a matrix with only 1s in a certain row. That will extract just the edge of an image. And then it gets a bit more complex, and then you detect things like the gradient and the texture and the gray level to detect different features. And your output is the final kernel that's activated. Let's say in this case, the combination of all these input kernels results in the dog class being activated. And what this convolutional neural network does, it takes the input image, performs a bunch of convolutions, and then predicts that the image is a dog. Now, where the machine learning part comes in, again, is the adjustment of these weights. So each time the input passes to an intermediate layer, it gets weighed by a certain amount. Think of it as sort of adjusting how important this feature is. For instance, if this, let's say, where my cursor is, I'll try the annotate tool. Let's say this kernel detects top right edges. If after optimization, all these edge branches are 0 weight, that's the neural network is saying, okay, after optimization, we decide that the top left edge is useless in this image. Right? So that's sort of how a neural network will learn. So now the question always comes up, well, what are these kernels or neurons, right? We always throw them around, but it's not really intuitive what they are. So this is an example of after the network, that dog filtering network is trained, what the intermediate kernels look like. So in this, what we did was we passed through the dog image and we took the output of that kernel. So this one will, for instance, this image will take out anything that's black will be ignored in the image. Anything that's white will be enhanced in that image. So for instance, this one will look at what's in the center of the image. It'll focus on the center of the image. And then your network will run and then decide which of these kernels are useful and which are not useful. So it's very high complexity, very incremental, but it's very, very effective at detecting complex things like image recognition. So now, do we always need a neural network? Because machine learning papers always talk about neural networks. Any Elon Musk interview, you'll see him talk about neural networks. It's always in the media, but no, you do not always need a neural network. So in clinical research, I would say even the majority of what's published out there is using the methods we talked about last week, like logistic regression, a support vector machine, or a random forest, because these not only are these more interpretable, they're also much less costly to run. A neural net, a convolution, for instance, a project I worked on, we had to use a convolutional neural network to extract the placenta from ultrasound. To train that network took 30 hours, whereas a random forest on clinical data takes about 2 minutes. So there's a high cost in using neural networks. And if we can avoid them, I suggest to avoid them. So this is an example of a random forest, right? This random forest, again, if you recall from the previous weeks, is where we make a flow chart of the variables. And then at the very bottom is an outcome that we predict or we classify the data as. Random forest is shuffling the variables around so that we optimize the accuracy of this flow chart. And this is a very common method. It's very interpretable. And if they have the same performance or within, say, 2% accuracy, I would pick a random forest any day of the week. So now we'll go through this. After. Actually, we'll go through this now. So here, these are some, this one paper that I found. And let me know if we can't see this. Let's see. Okay, so this one paper is an example of using machine learning on a clinical research project. So here, what I usually do in practice, honestly, I read the abstract. The introduction, usually people are just motivating their idea, but we all know that it's an important research project. So I read the abstract to see what their purpose is. So they want to, from an ECG, classify arrhythmia using the RR interval. And the way they do it is that they use a discrete cosine transform, and then, well, they do machine learning afterwards, but they don't mention it in abstract, which isn't that great practice. So now it's up to you to judge if this data is good or not. So if they name drop MIT here, so that people do that sometimes. This is all intro fluff. It's talking about ECGs, talking about premature ventricular contractions, bundled branch blocks. This is literature review. We're not that worried about that right now. This is sample ECG, and this is where they talk about how they transform their data. So remember in our second session, we said that sometimes the base data isn't that good. You have to transform it to something meaningful, such as removing noise from each ECG. So here they use something called a discrete cosine transform to transform the ECG from a time domain to a frequency domain. So you can see how strong the 60 hertz signal is, for instance. This is not that important. We're more interested in the machine learning part. So we read until we see something machine learning. Okay, here, growing ensemble random trees for classification is called random forest trees. So they're using random forest. Okay, so not a good look already, right? It takes them this long to say that they're using machine learning, specifically random forest, to try and classify if an ECG has an abnormal beat. Here they explain random forest, but that's not what I'm interested in. What I'm interested is if they did the due diligence to apply the method rigorously and then validate it rigorously. So you don't need math background to understand that. You need math background to understand if, for instance, they optimize it correctly and they use the correct math and the input output is correct. But for clinical research, even without the math background, you can critique a paper by looking at if they did the due diligence in data science. So this is still talking about how to make a decision tree. So now, so even up to here, they're still talking about the theory of decision tree, but I want to know their methods and the validation strategy. Okay, so now they're talking about the data. So they have 68 instances of LBBB, 30 instances of right bundle branch blocks, and 56 instances of normal. So in total, what's that? That's 154 images. not the greatest number. Now, the question is that how many features are they classifying with, right? Are they, once they use discrete cosine transform, what do they do with that? Because that's um, a series of data. They're not going to use that entire series. So that's already a red flag that they didn't talk about what features they're looking at, what specifically in that discrete cosine transform they're looking at. The amount of data is also not very high. So in the 100 range, usually you can't claim any sort of insanely generalizable accuracy. The most you can claim is a proof of concept saying this could work. Okay, now they say tenfold cross-validation. Okay, good. Cross-validation is always good, but tenfold means we're splitting the 158 into 10 bins. So each bin will have about 15 data points. It's okay. That's usually you want a bit more in each bin. So now what are they talking about here? 1, 5, 10, and 20 trees are constructed. They don't really explain what this means. So with background, I know this means the hyperparameter of the random forest. A random forest, you'd specify how many trees you initiate before you average all those flowcharts. So, but there are also other hyperparameters. They don't talk about what the why they chose this range, and they don't talk about how to optimize and choose the best range. So here, now they're showing classification accuracy in figure 3. So here, figure 3. So first of all, it's a Microsoft Excel plot that's not laid out very nicely. I don't know what these asterisks are. I'm guessing it's data point markers. So visually, it's not that great. So this is also the default name of when you plot something in Microsoft Excel. So here they have single tree accuracy, 5 trees, 10 trees, 20, and 30 tree accuracy. So this is actually believable because you get diminishing returns as you increase the number of trees that you're generating. But what we don't know is what do they mean by classification accuracy? Is this the accuracy on their training data or their validation data? Is it average across the 10 validation bins? We don't know, because if it's training accuracy, it's meaningless. You're building a model on the data set that you're testing the model on. That is highly illegal in data science and very, very bad. So it's not specified here, which is not very good. So even at this point, I would straight reject this paper. There is far too much this paper is missing. Okay, but for due diligence, let's look at root mean square error, same thing. Root mean square error of what? The test data, the training data? We don't know. Okay, and then, okay, the conclusion, okay, there's okay, oh, our study is very, very good, but it's not validated very well. Now, I don't doubt the method. Random forest is a great method. A discrete cosine transform can be a good method for analyzing ECGs. Better one would be Fourier transform, but it's not validated. They do not do the due diligence to verify if their method is correct or not. Right? They did not split into train test set and test them individually and show me the average and show me the confidence intervals. This paper is not very good. All right. So that's an example of a bad paper. So at this point, are there any questions? And then just for fun, I looked up the impact factor of that journal. I think it was 0.09, which makes a lot of sense. Okay. Okay, let's move on. So this is a really, really high yield diagram. So this tells you how accurate certain machine learning methods are and generally how interpretable they are. So the interpretability is more accurately represented than the accuracy. So a classification rule is, for instance, if hypertension is above this, immediately classify as coronary artery disease. And then linear regression, familiar with statistics, decision trees, k-nearest neighbors, graphical methods. These are very interpretable method, right? Decision tree, which we saw example last time, is creating that flowchart. And then there are things that are less interpretable, like a random forest where you have a lot of decision trees and then you average it using some rule. you see that neural network is really the least interpretable out of all of them. And a convolutional neural network, I put them maybe over here in like negative interpretability, right? But it's most accurate because you can sniff out highly detailed interdependencies between the variables. Downside is that it's also very sensitive. So if you change the input, sometimes it overfits to your data. So if you change it a little bit, it won't work. So the rule of thumb is pick the simplest thing that works. That is usually a very good bet. But for publication wise, reviewers really like it when you try a lot of 3 or 4 different methods just to show that it wasn't a fluke that your method worked. So now, this is so I'll show you an example of how sensitive neural networks are. So this is an example of a convolutional neural network. Let's say we're trying to recognize what these icons are. And this is usually what the diagram looks like. You take a part of the image, you do some calculation, and then you pass it through the next layer. So W is the weight parameter. So these are the weights in between the layers. So for instance, and then we adjust the weights and we optimize the weights to optimize the neural network. Now, the problem is that neural networks are very insensitive. For instance, in this image, the prediction was a speed limit equals 80 sign, but which is sort of close because it still predicts it as a speed limit sign. But in this image, there are only several malformations, and then the neural network just completely gives up. So now in these two images, there's something that was manipulated differently in these two images. But to a human eye, we both see that these two are both pigs. But to a neural network, what happened in one of the neural networks used in the study was that the left was predicted as a pig and the right was predicted as an airliner with 99% accuracy. Now, how did this happen? Well, the researchers purposely manipulated the right image by adding this sort of inhomogeneity inside. So these are very subtle difference within the texture of the image, but the subtle differences were enough that because the neural network goes so detailed that this completely screws up the network. It completely throws it off from recognizing any pig-related features. So this is a difficulty with neural networks. So in a clinical side, what this means is that make sure all your input data is consistent. Don't get one ultrasound scan from one sonographer and another ultrasound scan from another country using a different machine and lighting settings, right? The more consistent your data is, the better your predictions are. So this is an example, for instance, trying to classify these images as turtles or not turtles. So they're not always the most consistent, but they do a really good job when you prepare the data really well. So now how can we make it so that it doesn't make these errors? Well, there's 2 ways. Our input data should be consistent, and we should have a wide variety of input data. So the technique we talked about week 2 is data augmentation. That's when we take the original image and we manipulate it just a little bit, but we still use it to train the network. This is an image of a bird. These transformations they keep the key feature as a bird. So as a human, we still see all of this as birds, but we adjust it a little bit. So we add some impulse noise or add some frost effects so that the neural network is familiar with the changes, right? In the pig example, this is on a test set. So the neural network was not trained on this image, but now we're training on these variations. So that neural network will learn these variations like a human does. Like a human would learn that even if it's pixelated, we can still detect a bird. Intuitively, what this means is that we want the neural network to increase the weights of the key features, like having wings and having bird shape, and decrease the weights of non-key features, like forcing the branch to be brown color. This is an example of augmentation where you take the Eiffel Tower, you rotate it a little bit, and then you insert it into your convolutional neural network. So now, any questions at this point before we move on to the programming example? So in a disclaimer, Prash helped write a lot of this, and he loves Lord of the Rings, which is why he puts a lot of Lord of the Rings memes in. Okay. So we will go through Actually, I'll show, before that, I'll show a good paper. Okay, this is an example of a good paper. So this is, it's not, state of the art CVPR. So CVPR is the top conference for machine learning. It's like the New England Journal of Medicine for machine learning. Nature, surprisingly, is not that great of a journal for machine learning. So this is a project where they try to use deep learning to diagnose things from chest radiographs. Right, so they have 112,000 radiographs, which is a great number, great sample size, and then we have a lot of different classes for pathology, including atelectasis, hernia, fibrosis, emphysema. All you have to know is that there's a lot of different pathologies that we're trying to predict. So I'll just spoil it for you. They have great class balance. They have a lot of samples from each pathology except maybe hernia. So I would not trust the hernia prediction. So what they did is they use a convolutional neural network called DenseNet. It's an existing one out of the block box. So these researchers didn't invent anything new engineering wise. So what they did is that they took 420 samples of the radiographs as their validation set, and they balanced it really well to make sure that there's at least 50 cases of each pathology. And then they had some radiologists annotate these radiographs to use as a gold standard. Now, they evaluated using the standard evaluation metrics: area under the curve, sensitivity, specificity, predictor value, Cohen's kappa, which is evaluating the inter-observer agreeability. So this is the results. This is what the neural network predicts. For instance, there's some opacity here, and the neural network predicts some pathology here. But we're more interested in the quantitative results. So a perfect curve would be this top left corner and an area under curve of 1. But these are actually quite good, right? Except for hernia, because there aren't many samples. So when you see a curve that's very discrete like this, that should raise your suspicion. But for things where they have a lot of samples for, like consolidation, it has quite good sensitivity and specificity. And then it's much more easier to see it this way. So looking at the sensitivity and specificity, that's really what I looked at. Most of them are okay for effusion. They're not that great for nodule. But the point is that this study did really well on the due diligence to report honest results. Right. So now the question is, looking at this, well, what do we learn from this study? Well, we learned the study is quite good for things like effusion, not that great for nodule. So is it still useful? And this is a question you come a lot when you design and execute AI projects. Is it clinically useful? And is this useful science? Well, in the engineering world, we're always like, it's useful. It tells us something about if the math works in this application. But clinically, well, it's not as accurate as radiologists. It's mostly around the same accuracy within the confidence interval, but it doesn't beat the radiologists. And spoiler, with most studies, we don't beat radiologists yet. No, despite what you hear in these like cherry pick studies, on average, AI does not beat radiologists. But the benefit is that it reads 420 X-rays in 90 seconds, right? And radiologists would take much longer. So you can make an argument that, well, this is a proof of concept that we have this automated system that performs just as well as radiologists, but it's more efficient. So it can be used as a physician aid tool, or we can deploy it in low resource settings where they don't have access to radiologists, or we can deploy it in settings where you have to triage people, right? So it shows that AI can work in this scenario. It's not what we expect from the media where AI is taking over physicians. It's more has an angle where it sort of aids the current workflow and certainly has a place in the next 10, 20 years. And I think that's really where AI is going. It's not physician replacement, it's more physician aid. So that is the paper. So I'll post all this in Slack, the program example and the papers we reviewed. But let's run through the actual program. So what I'll do is that I'll share this to the chat, and you can run it as we go along. Copy this link here. So what we have, I'll send this in the chat first. What you'll have to do is, okay, it's in the chat. Once you open it, go File and save a copy in your drive, because you can't edit the copy on the screen. That's my copy. They'll save this program onto your Google Drive. And I'll give everyone about a minute to catch up with that. So again, what this is, we're continuing from last week's example where we took a breast cancer data set of imaging parameters, and we're trying to predict if the lesion is malignant or benign. Last week, what we did was we built a decision tree to do that. So a decision tree is here. This is the optimized decision tree with about 93% accuracy. And this is this is very interpretable, right? You look at the worst radius, and then you look at the concavity points, and then you look at texture. So this is very interpretable method, and clinicians love decision trees. Now we'll try using a neural network. So what we have to do first, again, to run this, click on the cell you want to run. It'll be highlighted in gray. And what you do is you can either click this play button to run the cell. So this first cell just loads the library. Or shortcut that I use is hold Control and press Enter. Now, again, in the past, in real life, I'd be walking around and guiding everyone through the programming. But because that's quite difficult over Zoom, we just have the program for you, and you can just run it. And if you want, you can take some of this into your own project and publish something, because this is crash build most of this, and it's really publication quality. So I'm going to run this first cell because I need to load all of these libraries. So this sklearn is the machine learning library called scikit-learn. And then these are libraries that help us visualize things. Now, this first part we did last week, we can skip. So we're going to go scroll all the way down to where we load the breast cancer data set. And that is right here. Okay, so this is where we want to load the breast cancer data set. So we can run the cell, Control Enter, and loads the data set. Okay, great. Now this is what we did last week. I kept this here, the output here for you to look at in your reference. Well, we're skipping all this. We're going straight to the neural network. This is a neural network. So this is what our neural network looks like. We're going to have 2 hidden layers with 5 or 2 neurons each, right? So, and it's going to, the input is going to be all of the breast cancer variables, which is like the concavity, the texture, the shape, the perimeter, measurements measured by the radiologist or radiation oncologist. And then these two are the intermediate layers, right? And then the output, final output, is a classification, 1 if malignant or 0 if benign, I think. And it's all programmed here. So what we do here is first we split the data set into a training and a validation set. So, and then we create the neural network by the function MLP classifier. So the typical, why is it called MLP? It's because back in the day, neural networks were called multi-layer perceptron, but unfortunately the name stuck. So what we have here, we call this, we want to create a neural network object, but we have to give it some input arguments. So one is what optimization function to use. Atom is the most common one. It's actually the most cited paper in like the last 5 years. So this is interesting fact. Alpha is how it's a hyperparameter, which again is a manual parameter we adjust. So alpha is how much the neural network will adjust the weights. Hidden layer sizes, this defines our hidden layers. Remember, we want a size of 5 and we want 2 layers. Max iteration means how many times we run before we call it quits. Verbose is asking if we want the neural network to spit out results every single time. We'll just say no for now. And random state is how we randomly want to initialize it. This one doesn't really matter. We just pick one arbitrarily. Okay, so now we create this neural network model. We want to fit it to our data, which we do by this function. We say we want to fit it on our training data. So X is our input, and then Y is our results. And then we'll look at our training accuracy and our validation accuracy. So it looks very simple because a lot of this is packed in already in the library. So we can just simply run this, so Control Enter. And our neural network has a training accuracy of 98% and a validation accuracy of 98%. Well, and if you remember, the random forest had an accuracy of, I think, 93%. So you can see the neural network is more accurate because it's able to model those complex interdependencies. If you're interested, this is the confusion matrix showing the true positives and true negatives. So it does very, very well, right? But it's not very interpretable. Like, what are you doing in between? What are these neurons doing? It's not as interpretable as a random forest. Okay, so now what we can do next is that we can do example of a convolutional neural network. So down here, what we're doing is that we're downloading a data set called the CIFAR-10. It's a data set containing images of planes, cars, birds, dogs, deer, animals. And the task that researchers have is they want to take this data set and try to predict what's in the image. So let's say a picture of an airplane. You want your convolutional neural network to predict that's the airplane. Right. This time we're using a different library. We're using the PyTorch library, which contains a bit more advanced tool. And here where we have to use a graphics processing unit because our central processing unit usually isn't powerful enough. GPUs are great at repeated tasks like this. So we're going to run this cell to load in GPU. Google usually provides a free GPU, but sometimes you have to select and change it so that you're using GPU. So here now it shows that I'm using GPU. Great. I want to download the data set first. So this is all just grunt work, just loading in the data. So in practice, you won't have to do this. Here, I'm just downloading the data. And then it shows me the progress bar here. And then we downloaded the data set. Now let's show some of the images here where we're using the NumPy library, which is a library in Python that allows us to manipulate images. We just want to show them. So there's no machine learning here. We're just showing them images. So these are the images, sample images in this data set. There's a ship here. There's an ostrich bird, a cat, and a car. Our task is to create a convolutional neural network that will predict these classes. So now, the hard part of a convolutional neural network is deciding what layers, how many layers you want and what do you want in those layers. Do you want a convolutional layer where you have matrix multiplication or a max pooling layer where you try to sort of decrease the image? You don't have to worry about that. That's an AI engineer's problem. And usually there are existing networks out there that perform really well. Like that chest X-ray paper we just read, they just use an existing neural network here. So here we just create a very simple neural network with these. These are the layers. So what this cell does is that it just creates this empty model that's not optimized yet. So I ran the cell and it's usually takes a little bit of time to run. Okay. So this is the neural network. All right, you have some convolutional layers, some fully connected layers. What we do next is now we want to train this neural network. Right? So here we're defining our loss function, which defines how much error we have. That tells the neural network what to optimize. Again, we're using the Atom optimizer, which is what most people use, with a learning rate of 0.001. That tells us how much the weights adjust. Okay, and then the thing I don't like about machine learning is that there's a lot of jargon. So in neural networks, things run based off epoch. An epoch is a full run through all the images. And you specify how many epochs you want to run. So here, let's just run 2 epochs. Otherwise, it takes too long. So within each epoch, we're going to run through the data and then compute the loss and then optimize based off the loss, right? You don't have to fully understand how the optimization function works. The gist of it is that it goes from the output and goes backward and computes a lot of derivatives to perform some vectors calculus optimization. It's known as gradient descent. That's the famous algorithm. But all we have to know is that it's optimizing. So let's run this cell. And usually this takes the longest. So a convolutional neural network for that chest X-ray data set would probably take 30 to 40 hours. Here we're only running for 2 epochs, so it should take a lot less time. All right. Now I think the last time I ran this, it took about 2 minutes. So feel free to ask any questions in the chat if you have. Get some water. All right. I know you said that you ran 2 epochs. How was running more than 5 lines of code? You don't run the entire epoch at once because that takes too much memory. You usually split up into batches, and then you run based off those batches. So now we're on our second epoch. Yeah. So in practice, we run this on a server at UBC in like some server room. We let run overnight or over 2 nights to optimize the neural network. And then once it's optimized, we take those weights. The weights are really what the model are. We take those weights, you plug it on USB, bring it to the hospital, load up your neural network, and then feed it new images, and it'll predict based off those new images. All right, should be finishing soon. I think there's one more step. Okay, so now we're finished training. So the neural network is optimized. We want to evaluate its accuracy. So let's evaluate it on a test set. That's what the cell does. It takes those test images, it feeds it through a neural network and looks at the prediction, and then compares it with the actual real outcome. So this is predicting the images, and then there's a line that will compute the accuracy. So the total accuracy on 10,000 images is 55%. So at first glance, you're looking at, well, the chest X-ray paper was 95%. Well, this, again, we have 10 classes, which is much harder task than predicting 2 classes. I'm sure if you only had cars and cats, you'll be able to have much higher accuracy in the 90s. So because if you just randomly guess, that'll be 10% accuracy. So what we can do next is that we can visualize some of the results. So here we'll visualize the accuracies for each class. So we see that, well, each class has a varying degree of accuracy. Dogs and cats are the worst. Planes are the easiest. And then at this point, when you're doing the research, you'll document these results, and this is probably what you'll present. But you see the downside is that, well, how do we interpret this, right? Why is a bird so much harder to predict than a plane? It's really hard to open up that neural network and look at the intermediate math and say, oh, it's because this matrix multiplication had its top row as something that's inaccurate, right? So it's very hard to interpret. But at this point, so we ran through an example of random forest, not random forest, a decision tree here, neural network, which looks like this, and a convolutional neural network. These are examples of common machine learning architectures you'll encounter, both possibly in your own research, but definitely when you're reading literature. So what I would suggest is that you don't have to be worried about the math in all of these architectures. Even through this course, you have some intuition of how they run, when they're applicable and when they're not. But most importantly, I think learning how to be skeptical of the results and how to properly critique the results, and knowing if it was a implementation with due diligence or not. I think that's the most important takeaway of anything in this course, and looking at all these neural networks and convolutional neural networks. So this program is, we'll also post in the Slack. In your free time, feel free to run it by yourself. Feel free to add or adjust code. You can even take it and use any existing clinical data you have to try and predict something. But other than that, are there any final questions before we finish the course? Give everyone about 2 minutes. I'll monitor questions for about 2 minutes before we close. I think if there's a diagram to take away, this is a really good diagram. Okay, well, if there are no questions, I hope everyone learned something and everyone enjoyed this course. Thank you all for participating. And for those of you watching the reruns on YouTube, we hope you enjoy something as well. I'm sure we'll meet again someday developing your own AI project or working with AI medicine in the future, because it is coming. It's not as scary as everyone thinks it is, but it is coming. And with proper preparation and knowledge, I think all of us will move medicine further and push the field forward. So thank you, everyone. And we'll see you all in the future.